Jnanam paramam dheyam. Knowledge is supreme.
So, I have tried to introduce the outer product here, which is an operator, but this outer product, if you see, this outer product, if you see, it is the outer product of the same state. What is the property of a projection operator? Let me ask you this. What is the property of a projection operator? If you do it twice, it will be the same. Any number of times you do, it's going to be the same. Can we verify that here? Let's take P1 squared. What is P1 squared? P1 squared is, P1 is phi 1 phi 1. Okay. You will also have a phi 1 phi 1. But what is this? We have taken a orthonormal basis. So, that is 1. So, this is same as phi 1 phi 1. That is the property of a projection operator. I am not, sometimes I do not put the hat, but now from now on you should know whatever we are doing, when I write an outer product, it is an operator. So, this is the property of the projection operator. What are its eigenvalues? Now, you can give in the two-dimensional vector space, you can rewrite this as a 2 cross 2 matrix, right. So, let us write, suppose phi 1 is taken to be 1 0 and phi 2 is taken to be 0 1. What is phi 1 phi 1? One 0 0 0. What are the eigenvalues of this? 0 and 1. Right. If the state is in that subspace, it will get projected with the same, it will be as it is. If it is not in the subspace, it is going to be 0. So, that you can also satisfy from here P1 squared minus P1, you can solve that equation. Can rewrite P1 squared minus P1 as P1 squared minus P1 equal to 0, which implies P1 is either giving 0 or 1 as eigenvalues, right. So, this condition, when I write, this is a product of two operators, this condition, this will either tell me that P1 is 0 or P1 is equal to 1, that is all I am trying to say. And it should also satisfy P1 squared equal to P1. With these constraints, these are the only possibilities. Okay. So, that is the beauty of this projection operator, where this outer product phi 1 phi 1 is 1 0 0 0, then the other product phi 2 will be 0 0 0 1. So, what is phi 1 phi 2? Phi 1 phi 2 is not a projection operator, but it is still a 2 by 2 matrix. What is that 2 by 2 matrix? Someone can help me? It is 1 0, which is a column multiplying 0 1. Is that right? Similarly, what is phi 2 phi 1? 0 0 1 0. So, what have I tried to do? I have tried to show that the 4 possibilities of outer product which I can write for the 2 bases, 2-dimensional vector space, they can be given, the outer product can be given a 2 cross 2 matrices with only one entry which is non-zero. Okay. So, this appears like the 1-2 element which is non-zero. This appears like the 2-1 element which is non-zero. And the earlier ones were the diagonal elements, 1-1 was non-zero, right? 5-1, 5-1. 5-1, 5-1 is 1-0-0-0 and 5-2, 5-2 is 0-0-0-1. So, this should kind of tell you something. Any 2 by 2 matrix which you write can be represented in terms of this Dirac notation, where you will have 4 possible basis states with 5-1 and 5-2 in the 2-dimensional case. So, let me write that. So, if you take some operator A, you can rewrite a representation for this in this 2-dimensional vector space as some A11, A12, A21, A22. I can also rewrite this as A11, 5-1, 5-1 plus A12, 5-1, 5-2, 5-2 plus A21, 5-2, 5-1 plus A22, 5-2, 5-2. This is also correct. Write this compactly as summation over I comma j, which is 1 to 2, Aij, phi I, phi j. So, just like we wrote a state psi as summation over I Ci phi I can write any operator. This operator could be position operator, momentum operator, angular momentum operator, all possible. By operator I mean anything which you see in the observable. So, they can be given an operator in quantum mechanics, and they can be defined just like phi I or the basis for the states. The outer product will be the basis for the operators. How many will be there in n-dimensional vector space? N squared basis. And from here can we extract what is, let us say what is A11. If I want to find what is A11, how will I go about it? So, let us do that. So, let us take phi 1 with A operator phi 1. If you do this, what do we get? This left hand side angular bracket, the bra, will only give non-zero with which 2 terms? Only with the first term and the second term. Third term will be 0 by the orthonormal property, right? The phi 1 if I operate, phi 1 phi 2 is 0. Similarly, phi 1 phi 2 is 0. So, these 2 terms will be 0 by putting the bracket, the bra vector phi 1 if I put on both sides, this is going to be 0, these 2 terms. If I put the ket phi 1 after that, that will operate on this state and it will, what happens to this term? Phi 1 will be 0. So, what do we get from here? The only non-zero element will turn out to be A11. Okay. So, what have I tried to present here is that If you have an abstract operator and an abstract basis states, you can find the components of this abstract operator, just like Ci when I wanted to find, Ci was phi I with psi. So, you take the inner product of phi I with psi. In the context of operators, if you want to find these coefficients Aij, you have to take phi I, A operator, phi j. That is it. Any operator, Hamiltonian operator, we could write, and so on. So, the operators also has a basis. The bases are this outer product of this basis vectors. So, there will be n squared basis, and you can write any arbitrary operator as a linear combinations of these outer product bases. So, suppose I give you that Hamiltonian is given to be epsilon 1 phi 1 phi 1 plus epsilon 2 phi 2 phi 2. Suppose I give you this. What does this mean? These two are like the projection operators. There are no cross terms. So, this will be the matrix representation for this can be written as a diagonal matrix with the off diagonal terms being 0. So, you need to be able to read, given any operators in this notation, what actually it means if you put it as a matrix operator, matrix representation. You should be able to read from there whether it is diagonal, whether it is off diagonal. But once you put it in this notation, finding the eigenvalues and eigenvectors, you already done, right, in your math course. Any 2 by 2 matrix, if I give you A, B, C, D, how do you find the eigenvalues? So, A minus lambda I, determinant of that equal to 0, you can find the eigenvalues from that, right. So, it will give you lambda 1 and lambda 2 as eigenvalues, which is given by this matrix is A minus lambda I, determinant of that has to be 0. Then you solve this and you find what is the 2 eigenvalues. And once you know the eigenvalues, you know how to find the eigenvectors. This is a compact Dirac notation for a diagonal operator, but whatever I write there for a finite dimensional vector space, you can try to rewrite it in matrices and you can work with what you know from your matrices. So, what are the eigenvalues of this operator? If I ask you, it is very trivial. Epsilon 1 and epsilon 2 are the eigenvalues and the basis states are phi 1 and phi 2, which is 1 0 and 0 1. So, this can be a trick question asking you find the eigenvalues and eigenvectors. There is nothing to work out. But if I give you an off diagonal matrix, you need to do a little bit work, because once I have this off diagonal matrix, it is no longer, you have to find out what is the eigenvectors and the matrices. Okay. So, let me just try to, okay, so this is what I went through just now, that you have phi 1 phi 2 which is orthonormal basis and psi 1 psi 2 which is non-orthogonal, and you can do a Gram-Schmidt orthogonalization, and in the process you see a phi 1 which is the nothing but this outer product is nothing but a projection operator projecting onto a subspace phi 1, and you subtract that out, and then what you get is the state which can be the orthogonal basis to the phi 1. So, and this is what we called it as a projection operator, and in 2 dimension we can write 2 projection operators whose sum is an identity operator. Okay. So, for an n dimensional vector space, you could write projection operators n of them, and the sum of those projection operators will be turning out to be 1. If it is not 1, what does it mean? Suppose it is not 1. Excellent. So, you have not spanned the whole space, and it's not, you have not found the complete set of basis states, right. Suppose you are in XYZ and I give you only P1 and P2, and I say that there is only phi 1 and phi 2, and if it is not equal to 1, you know that it is not spanning the whole space. You have to have one more, then this is not a complete basis set. You have to give, for a 3-dimensional R3, I have to give you I cap, j cap and k cap. If I just give you I cap and j cap, it's not complete. You all agree? So, this condition which we write, this condition that the sum of all the projection operators of a given basis set being identity is what is called as a completeness condition. Okay. This is the completeness condition, and we need this, without which we cannot work, we cannot make progress. A basis set, if I say it is a basis set, it has to satisfy this criterion. So, if I say orthonormal basis set, then phi I summation over I from 1 to n has to be an identity operator. This is a, if I call this by definition a basis set, then this has to be satisfied. This is called completeness condition, and you have to also, once you say it's orthonormal basis, it's understood that this is delta ij for all I comma j, which is 1 to n. What else? Any arbitrary operator will be rewritable as comma j, some aij coefficient phi I phi j, and any arbitrary state psi can be written as this takes care, basis set includes the span and the completeness condition and this criteria. This is clear? Playing around between Dirac notation and your familiar matrices in a 2 cross 2, 2-dimensional vector space and 2 cross 2 matrices. If you are clear about this, you can do any 3 cross 3, n cross n. What happens to functions of operators? Suppose I write an operator A as summation over I comma j, aij phi I phi j. What happens to functions of operators? Suppose I want to do this. That's one question. And then you can extrapolate it to exponential of IA operator. What it is? A squared is repeating this. You can put two different indices and do this, right? A squared will be summation over mn, a mn, and then you will have a phi m, phi n, and then summation over ij, aij, phi I, phi j, and then what do you have to do? These are numbers. Phi n, phi I will be, what will that be? Summation over mn, ij, take it out, summations, take all the scalars out, and then what do we have? Phi m, then phi n, phi I, phi j. What is this? It's delta ni. So, you will have summation over Mn Ij delta Ni Amn, Amn Aij, then phi m, phi j. So, wherever n is there, I can replace it by I, and one summation of I is gone. Yeah. So, this thing you can write it as A squared, the mjth element, right. So, you can actually see that if this is A, then this becomes a function of A squared, function of that operator, this coefficients. So, this is what you are trying to see. So, you can try and do this for a general. So, just to tell you what is Hermitian, what have you learnt about Hermitian operator in your first course? An operator operating on a psi of x, if it gives you A times psi of x, then you say A is a eigenvalue. For Hermitian operator, what is the requirement? This is an eigenvalue equation. A is the eigenvalue. If you want to call A to be A, the capital A operator to be a Hermitian operator, then A has to be real. When you do an expectation value of d by dx operator, what happens? You can show this to be imaginary. Have you tried this in your particle in a box? Please do this. Particle in a box, take the particle in the first excited state or a ground state or any state. Find what is expectation value of d by dx. Please do this. That's why d by dx is not a, it's giving me expectation values which are imaginary, which is not an observable quantity. So, that's why we do this I d by dx. Of course, with dimensional things you have a h cross also with a negative sign. This will be real. This, I am sure you would have done it in one of the assignment problems. Expectation value of del by del x is imaginary. Have you done this or no? If you have not done it, please do it. It's not difficult. Please try and prove that the expectation value of the del by del x operator for a particle in a box, if you try to do this, it is imaginary, whereas minus IH cross del by del x is going to be real. So, if you want to call an observable, the expectation value of the operator should be real. So, d by dx operator expectation value is not real, it is imaginary. So, for you the momentum operator is minus IH cross del by del x, because that expectation value will be real. So, this is something which if you know, then we can go to this. I will do this on Wednesday after you come back from your break, and then the hermiticity condition I will tell you. Okay. Let me stop here.